infinite radius. It can certainly happen that the radius of convergence is infinite. Well, let's consider this power series. The sum n goes from 0 to infinity of x to the n divided by n factorial. Let's try the ratio test. So here we go. The limit n goes to infinity of the n plus first term, so x to the n plus 1 over n plus 1 factorial, divided by just the nth term, which is what's displayed here, x to the n over n factorial, and absolute value of that. Since I'm checking for absolute convergence with the ratio test, I can simplify this a bit. This is a fraction with fractions in the numerator and denominator. This is the limit n goes to infinity of x to the n plus 1 times n factorial in the denominator of the denominator, put that in the numerator, divided by x to the n times n plus 1 factorial. So I've just got a fraction, but I can simplify this a bit too. This is the limit n goes to infinity. I've got x to the n plus 1 over x to the n, just leaves me with an x in the numerator. And I've got n factorial in the numerator and an n plus 1 factorial in the denominator. Well, n plus 1 factorial kills everything here, right? N plus 1 factorial is 1 times 2 all the way through n plus 1. And that contains all the terms in n factorial. So what I'm left with is just an n plus 1 in the denominator. Now what is this limit? X is just some fixed quantity. It doesn't depend on n. But what's the limit then of some number x divided by n plus 1, n going to infinity? Well, this limit is 0. Right? It doesn't matter what x is. If you take some fixed number and divide it by a very large quantity, you can make this as close to 0 as you'd like. So this limit is 0, 0 is less than 1. And that means by the ratio test, this series converges regardless of what x is. So what's the radius of convergence? Series converges for all values of x. And that means the radius of convergence is infinity. And in the not too distant future, we're going to see a very surprising result. We're eventually going to see that this series is in fact a complicated way of writing down a function we already know. This is just a complicated way of writing down the function e to the x. Meaning that if you plug in specific values for x, say x equals -1, you'd get that the sum n goes from 0 to infinity of minus 1 to the n over n factorial is equal to e to the -1. It's equal to 1 over e. And by choosing different values of x, by plugging in different specific values of x, we can generate a ton of really neat series. Like here's another example. I mean, just the fact that the sum n goes from 0 to infinity of 10 to the n over n factorial is, well, according to this, that's just e to the 10th power. And that is really cool. But let me warn you and share a bit of the philosophy of power series with you. Yes, by plugging in specific values of x, you can generate a ton of interesting examples. But power series aren't just a way of generating a bunch of series in isolation. Part of the joy of power series comes by thinking of power series not as a mechanism for generating a bunch of discrete examples, but as a way of collecting together a whole bunch of interesting series that depend on a parameter x.